You're welcome. I'm David Pomeranki, professor at the Institute of Electronics, and we're going to make a short video which qualitatively helps you to understand what a mode-steered chamber is. And this is preparation for a mode-steered laboratory. Imagine you want to measure the radiated emissions of this electronic device, this laptop, or you want to measure how robust is this laptop if strong electromagnetic waves impinge on it. There are multiple ways to do it, and the classical way to do it is the following thing. You take an absorber chamber, so it has absorbers here, it shields here, and you have a table in there, usually a wooden table. You would put the laptop on here, and then you place an antenna here. The antenna connects to a spectrum analyzer, and then on the spectrum analyzer you would see the emissions from the laptop. Of course, you may move the antenna up and down, you may rotate the laptop, and you maybe change polarization. So it takes quite a while before the measurement is done. Or if you wanted to measure how robust it is, if we have strong electromagnetic wave coming, then you would not use a spectrum analyzer, you would disconnect the spectrum analyzer, but you take a signal generator here, an amplifier like 100 watt, and then you connect the amplifier to the antenna and radiate electromagnetic fields on here. Now you have to sweep through all the frequencies. You again have to bring the antenna up and down, change polarization, rotate the laptop. It takes quite a while, but that's the classical method to do these experiments. A mode-steered chamber can achieve the same much faster. Okay, well, this is our mode-steered chamber. What is a mode-steered chamber? Well, it's a metal box, just metal. It's like a tin can. Of course, we have a door we can open and close. The door has a shield, so when the door is closed, this room is electromagnetically shielded. So inside here, you probably wouldn't get any cell phone. Normally, there's nothing in the chamber except this object. I'm going to explain it in a minute. Here is some electronics right now in the chamber, which this is for a different experiment. During lab time, this will be removed. Now, what is a mode-steered chamber? A mode-steered chamber is a fully reflective chamber. So if a wave comes, electromagnetic wave to the wall, it bounces off the wall and then hits the other wall. Now if the frequency is right, we will get the first mode. The first mode would be like that. The first mode. Or the second mode would be like that. And you can imagine that in this chamber, if the frequency is high enough, there are many, many modes, because the wave can reflect in this direction, diagonal. So there are many, many modes in this chamber if the frequency is high enough, and high means that the walls, the separation from wall to wall or ceiling to bottom is like 2 or 3 lambda large. Now, if you put a DUT in here, so my laptop, then the laptop has its own radiation, but the radiation may not couple to the modes well, because for some modes it's the right E and H field, for some modes not. So we have to change the modes here inside the chamber so that statistically all modes exist. And this is done by the mode steerer. The mode steerer is just a metal piece which moves. And what happens when the mode steerer moves, for every position of the mode steerer, the mode composition inside is different. And so in the end, what happens? You put the laptop in, and let's say you measure the electromagnetic field here, and you average over one rotation. Then you get a certain value at 500 megahertz. And then you do the same at another location. And at another location, it turns out statistically, so if we average over one rotation, the electric field strength you measure at every spot inside is the same. So we don't know which direction the laptop radiates. We don't know that. But we know how much it radiates simply by putting it in and averaging over one rotation. Then we basically know the radiated emissions from the laptop. For immunity, one could do the same and could put the laptop in here, put an antenna in here, drive power into the chamber, and then modes are set up. And if we change the modes, in statistical average, the laptop would get waves from every direction and every polarization over, for example, one steerer rotation. Okay, here's a little illustration of an experiment we're going to do later, but it's also good to talk about it on the whiteboard. This is our chamber, the mode-steered chamber, and I just draw one mode and 2 modes. I just repeat what I just showed inside the chamber. Now, think about the following. We do an experiment. We take an antenna, and we're going to take a bow tie antenna, which is just a triangular piece of metal, You won't see the antenna, you won't see the bow tie, the metal, but we put the metal between the styrofoam. This is one of the bow tie antenna. And let's say we take power from the network analyzer, we send power to the antenna, and some power will be radiated. These antennas have no loss. But some powers will be reflected back into the network analyzer because the antenna, for example, is too small. And if you look at the ratio of forward power and reverse power or reflected power, one can call that VSWR, or one can call it S11. And this is an S11 plot of such an antenna. S11 frequency 100, 200, 300 megahertz. And at low frequencies, the antenna is too small, it won't radiate. And then it starts to radiate, and then it has some good SWR, let's say minus 10 dB. That's sufficient. So now we have this is sort of the SWR if you take this antenna into free space. Let me describe the modes of the chamber a little differently. I'm making a diagram where frequency 100, 200, 300 megahertz, and I draw some amplitude here which associates to the modes. For example, that could be the average field strength if you put 1 watt in. Now, at low frequencies, this chamber has no modes. But the first mode is about, I think, 144 megahertz. And then there are very few modes here. But at higher frequency, we have very many modes. Thousands of modes per megahertz. And if you look at a mode has a center frequency and a width. The width relates to the Q factor of the chamber, high Q factor, narrow width. The Q factor is about 500 or something of this chamber. And so here the modes are separated. But here the modes are so dense, they're all overlapping. Now if you take the antenna into the chamber, yeah? If you take the antenna into the chamber, of low frequency, the antenna cannot radiate, it's too small. But then if you put it inside the chamber, you would see, aha, here it couples to the first mode. And only if it couples to the first mode, the energy can be transferred from the antenna to the chamber, and in the chamber it's converted into heat. You would see one mode here, and then you may see a few modes here. But at higher frequencies, the mode density is so high that the antenna reflects no power or little power because it's like free space. At every frequency, if it's high enough here, there is a mode. And so on average, it sees like a free space environment. Now let's look at the setup here. This is the mode steer chamber, and we have a network analyzer here. The network analyzer shows S11, so the reflection coefficient, and we start at 30 megahertz and we end at 300 megahertz. And we run a cable here to the chamber, go through the wall, come out here, and right now nothing is attached to the cable. So if nothing is attached to the cable, all the energy will be reflected, and that's what we see. We see everything is reflected, and we did a calibration, and the calibration takes care of all cable loss. So we put a calibration plane here, and we see full reflection. Now let's attach an antenna. This is the bow tie antenna here. So we have one piece of metal here and one piece of metal here. And as we use aluminum foil, we put it in styrofoam. Let's put the bow tie antenna on here. Now it's on. And let me just hold it here somehow in free space. And of course, the wall reflects in the room, so we see changes. But we see in general, the antenna starts working around this frequency. This is 5 dB a division, 5, 10, 15. 5 dB a division, about 130 megahertz or 120 megahertz, the antenna starts to move. And so at this frequency, the chamber doesn't have a lot of modes. Outside the chamber, the antenna would still show its reflection coefficient pretty much like free space, but the room is of course not free space. So we saw that the reflection coefficient of the antenna depends on a little bit where I move it in this room, because the room has reflections. So I took an average of it, and the average is the blue trace. So I took an average while I moved the antenna. So I put the average in the background trace, the blue trace. And now I want to put this antenna inside the chamber to see how the reflection of the chamber influences the antenna. The antenna is in the chamber on styrofoam. So this is electromagnetically transparent. And here I put the antenna on and we run the cable here and we go through and come out here. So let's close the chamber. And now let's look at the screen. So what do we see here? The blue is the background trace. This is the reflection coefficient of the antenna in free space. And here we see some frequencies where the antenna couples to modes. There are not many modes here. They add couples to modes. By the way, I don't know why this mode is here. But now we don't rotate the steerer. So we see modes, but we see individual modes and they don't move because the chamber is not moving. Let's turn on the steerer. Okay, now the steerer is on and we see all the modes randomly moving. Yeah, let's turn on average. So let's look at the data. We see at low frequencies there's full reflection. We see one mode here, and I do think this mode is actually caused by the cable length. That's the resonance of the cable which connects from the antenna to the wall. One could, for example, change the cable length and find out. But pretty much all reflected. But above this frequency here, we see the yellow curve approximately starts to follow the free space curve. So the antenna is radiating rather well in this range up to 300 megahertz. Little exception here, maybe some little exception here. But in general, we see that the chamber acts, allows the antenna to radiate pretty well. It's not fully reflected. Most of the energy couples into the chamber. And what we could do, we could go to a different antenna position and see how the data looks like. So I put this in a memory. So now I will put the antenna up vertical. Okay, now we put the antenna up vertical and averaging is going on. And we see this first mode doesn't couple so strong anymore. I think this is the cable, the length of the cable. But here, in average, we see somewhat similar behavior towards the different position of the antenna. So we see that the mode density of the chamber is high enough that we radiate into the chamber well. So we changed the instrument. Now we have a spectral analyzer here, but the spectral analyzer has two connectors. This is a spectral analyzer with tracking generator. So it has an output and receives. So if we, for example, receive at 1 gigahertz, the output is 1 gigahertz. So basically, if I connect them with each other with a low-pass filter or an attenuator, I can see the frequency response. And the frequency response is now we set start to 800 megahertz, stop to 3.2 gigahertz. And this is basically the coupling S21 from here to here. And we put a different antenna type here. Now, we have two antennas on each cable, and this is what's called a Vivaldi antenna. It has nothing to do with the composer. Nobody knows why it's called Vivaldi, but this is an antenna which excites a signal here, and the signal expands here, and by the way it's made, it can radiate. And this antenna goes from 600 megahertz to 12 gigahertz. Now, if we take both antennas and point them at each other, like now, then they couple very well. You see the signal on the spectral analyzer. Now I don't point them at each other. Or now I rotate, I make them cross-polar. So one is vertical polarized and the other is horizontal polarized. We put one antenna maybe here in the chamber and the other antenna we put here. So the antennas don't see each other directly. And now we can do an average to look at the coupling of the antenna in average. So we turn the steerer on. We close the door. And now we look at S21 and we look at the average. So I have to go trace. Let's say trace 1, type. It doesn't make a difference, video, power, average. Okay? And so now we have an average coupling between the two antennas for one antenna position. And the claim is if we change antenna position in the chamber, the average should stay about the same. So let's put this in memory. We put it in freeze. We open another trace and we look at the trace. And now we'll change the antenna position inside the chamber to see if the new average is similar to the previous average. So I change this antenna position to here. I change the polarization. And now let's turn on the average here. Trace 2, we do video average. And we see that although we change the antenna position drastically, in statistical average, the coupling between the antenna is the same, because both couple to very many modes, and the modes are so dense that they overlap.